before we dive into what acids and bases actually are and their various definitions of them, let's take a minute to think about what we already know about them and where we see them on a daily basis. We looked at on Monday in class at what electrolytes are and sort of another demo of what happened when that concentrated sulfuric acid reacted with the T-shirt. And we saw in both of those cases there's something that's going on in the solution. The electrolytes, we have a substance that dissolves into an aqueous solution to conduct electricity. An example of that would be the sulfuric acid, which we didn't test, but we saw 0.1 molar hydrochloric acid being conducting electricity. The sulfuric acid, then, the idea with that one was that there was a reaction that was forming. That acid was actually causing something to change in the fabric. So we know there's a lot of acids and bases in our everyday lives. Obviously not 18 molar sulfuric acid we don't have sitting around the kitchen at home. But we do have quite a few other common compounds that we have in our daily lives. So to think about a few, we know that in fruits there's citric acid. In milk we have lactic acid. There's a lot of household cleaners that have hydrochloric acid in them. Right now, as you're sitting and listening to this video, in your stomach, there is also hydrochloric acid. There's vinegar. That is a dilute solution of acetic acid. And we also know there's batteries. Battery acid is sulfuric acid. And in soda pop, there is carbonic acid. Bases are slightly less common, but still there's a lot of them around. We have in kitchens, most kitchens have at least one container, if not more, of baking soda. Baking soda, which is a compound called sodium bicarbonate, NaHCO3. There is bleach. Bleach is a base of sodium hypochlorite, so that would be NaOCl. Ammonia, which in solution forms ammonium hydroxide. Ammonium hydroxide. A lot of antacids are various hydroxides, weak bases. We have things like magnesium hydroxide, aluminum hydroxide. Oops, that'd be a 3. Various things like that. And we have lye, and a lot of drain opener. Those are sodium hydroxide compounds or solutions. And then there's a lot of soaps as well. Very strong soaps are other hydroxides, mixtures of sodium and potassium hydroxide, things like that. What we know about these, if we think about what you see there, those acids, and thinking about properties thereof, we know acids are depends on the concentration as well. But properties of acids, we know they are caustic to skin. They are corrosive to metals. A lot of them taste sour. Think about a lemon or a lime. They neutralize they neutralize bases, and they have a pH, I'll put it up here, a pH of less than 7, a low pH. So pH is typically in the 0 to 7 range. If we think about bases, let's give myself a little more room here. If we think about bases, what we know about bases, they are also caustic to skin. They actually react with your skin to form a soap, so that ends up being slippery. So if you're working in lab with bases and you start to feel slippery, that means your base is actually turning your skin into soap, so you'd want to wash that off. They taste bitter. They neutralize acid. And they have a pH in 7 to 14 range. And we'll talk more about what that means here in a minute. So we have a whole bunch of places where acids are. We know what they are. And we see here that we can see our properties of them. But what actually is an acid? There's actually 3 theories about what acids are, and each becomes a little bit more broad-reaching, a little bit more inclusive. The first theory of what acids were, acid-base theory, came from Arrhenius in 1887. And what he said an acid was, is an acid is anything that produces hydrogen ions, or H+, in a water solution. So if you could dissolve something like HCl into water and you got H+, that was an acid. And a base was anything that produces hydroxide, Hydroxide, hydroxide ions, which are OH- in a water solution. So that would be something like sodium hydroxide, NaOH. So there are a lot of acids, a lot of compounds that do produce hydrogen ions, but this definition of a base is actually fairly limited. If we scroll back up and even look at some of the examples we wrote, like ammonia, ammonia we know is NH3, but it's a base. It doesn't actually contribute hydroxide ions to solution. So what Bronsted-Lowry did in 1923 is they redefined what a base is. And this really is the definition. The Bronsted-Lowry definition is the one that most chemists use until you get into a lot of biological systems. The Bronsted-Lowry definition, an acid is, for all practical purposes, the same definition that Arrhenius used, is we say this is a proton donor. Well, what's a proton? Think about a hydrogen atom. A hydrogen atom, we know, is one proton in the middle with one electron zipping around the outside. Well, a hydrogen ion, as Arrhenius defined it, a hydrogen ion loses that electron, which means what's left? It's a proton. So a hydrogen ion really is nothing more than a proton. So the Bronsted-Lowry definition, a proton donor is the same as a hydrogen ion donor. It's anything that you can put into solution that gives up a hydrogen ion or a proton. A base, however, instead of producing hydroxide ions, a base, we use the definition that it is a proton acceptor. So anything that can accept those hydrogen ions. So let's make a little note over here. Proton equals hydrogen ion, or H+. So anything that gives an H+, that's an acid. Anything that takes an H+, that's a base. So if we take a look here on our next page now, a proton is a hydrogen ion, H+. The proton is never found free in solution, but actually combines with the water to form the hydronium ion. So in solution, the H+ exists actually as the hydronium ion, H3O+. So when you see these two things, they mean exactly the same thing. And you need to remember, be comfortable flipping back and forth between the two. Both H+ and H3O+ mean the same thing, but in solution, it is existing as the hydronium ion, H3O+. So for example, if we have sulfuric acid, H2SO4, reacts with water acting as a base, we form this conjugate acid, as we call it over here, H3O plus, and this HSO4 minus. So they're labeled conjugates, acids and bases, because they go together in a pairing. The conjugate base is formed, a conjugate base is formed when the acid in that equation loses a proton. So when it loses that H plus, it becomes what we call a base, and because it is, they're related to each other. That's where the word conjugate comes into play. So the conjugate acid then is formed when the base gains a proton. So if we look into our examples here, what we want to be able to do looking at any equation is identify what is the acid and what's the base, and then on the right side of that equation, on the product side, what are the conjugates. So using our definition of the hydrogen ion donor is our acid, hydrogen ion acceptor is our base, if I look between NH3 and NH4 plus, that gained a proton, which means NH3 acted as a proton acceptor. So that is my base, and my ammonium is my conjugate acid. Then water, H2O, went to OH minus, so it lost a proton. So that is going to be my acid. It donated a proton, donated an H plus, and the OH minus is the conjugate base. Here we have another example, HC2H3O2, that's acetic acid, goes to on the right sodium acetate. So this would be my acid, and then on the right, sodium acetate is my conjugate base, and my NaHSO3 would be the base because it gained a proton over here on the right, and that is now the conjugate, there we go, conjugate acid. Then we have our last example, Na, and remember, you should be familiar from thinking about these compounds from before where they split. The Na is given up, or let's see, no, here, let's look at the HCl. HCl, I know that is definitely an acid. It gives up the H plus, it gets the Cl minus, and the Cl minus, so that is over here on the right, this must be there for my conjugate base. And then the other ones, sodium, H2 phosphate, that's going to be the base because it gained a proton over here, so that would then be my conjugate acid. We're not going to use the last theory here much, the Lewis theory. It really is more of a biological application, but acids and bases, if we think about all our biological acids and bases, they don't even fit very well into our Bronsted-Lowry definition. So we had to get even more general. The Lewis, you recognize Lewis's name hopefully from our Lewis dot structures, which we have here on the bottom of the page. And the Lewis theory really is, as the dot structures are, all about electrons. So we still have donating and accepting, but it's sort of flipped from our Bronsted-Lowry. An acid is an electron pair acceptor, and our base is our electron pair donor. It still works with all of the other acids and bases. It's even a broader definition. We're not going to use it much, but it's good to have knowledge of sort of what it entails. So if we think about our three acid-base definitions, we have our Arrhenius acids and bases, which is a very limited set. We then went a little bit more bigger, so we have Bronsted-Lowry acids and bases. All of the Arrhenius are which Bronsted-Lowry And then our biggest definition is our Lewis acids and bases, which